All right. How's everyone feeling today?
Totally awesome, sir.
Okay, wonderful. So today's question is, how can rotational motion problems be solved using conservation of angular momentum? And if we're going to use conservation of angular momentum, we need to know what angular momentum is. So I'm going to go to this PowerPoint slide here. So the first question is, what is angular momentum? Before we answer that, let's go back and just think about regular momentum. Sometimes regular momentum gets mixed up with inertia. So they're very, very closely related, but they're not exactly the same thing. So take a moment to look at these two statements and figure out which one is defining momentum and which one is defining inertia. Okay, share with your nearest neighbor which one you think is which. I'll listen in.
No, but like, think of the basketball with the water. While you're moving it, it's so hard to change its
direction. Same, I agree with you.
Okay, here we go.
Basketball.
Inertia indicates how difficult it is to change whatever an object's doing. If it's moving, it's hard to change how it's moving. If it's at rest, it's hard to change whether it's at rest. Momentum, on the other hand, is an indication of how difficult it is to stop an object. Like a large tractor trailer fully loaded with potatoes. If that large tractor trailer is at a standstill, it would have a lot of inertia, but it wouldn't have any momentum because it's already stopped.
Mr. Selinsky?
Yes?
What was the letter again that indicates momentum? P.
P. So here we go now, rotational style. Which one is angular momentum and which one is moment of inertia, which is the special way of saying rotational inertia. Let's take a look. Moment of inertia indicates how difficult it is to change an object's rotation. Angular momentum is an indication of how difficult it is to stop the rotation. So what we want to do now is we want to review like the formulas for momentum and for angular momentum. So what you need to know is that inertia is indicated by mass alone. A lot of times they'll give you like the mass and the velocity of four objects, and they'll ask you which one has the most inertia. You don't even have to consider the velocity because it only depends on the mass. Inertia and mass are directly proportional. Momentum, on the other hand, symbol P, is equal to mass times velocity. And the units are kilograms times meters per second. Now, rotational style. Moment of inertia, symbol capital I. If it's just a point mass, like a yo-yo swirling on a string, it's just mr squared. But if it's a cylinder or a sphere, it could be 1/2 mr squared or 2/5 mr squared. But today's lesson is all about angular momentum, right down here. So what I want you to do is take a second look at this regular momentum formula and see if you could write down the formula for angular momentum. Call me over if you have a. There you go. You got it.
Yeah.
There is. I just haven't told you yet.
I was right.
It's the exact thing that we.
What do you mean?
Remember the rotational version of mass. Instead of m times v, it's going to be the rotational version of mass times the rotational version of velocity. And what's the rotational version of mass? I. And the rotational version of velocity? Omega. So angular momentum is equal to I times omega. The symbol for angular momentum is kind of bizarre at first. You just get used to it, not sure of the reason why. It's a capital L. So capital L equals I times omega. And the units are basically what you see is what you get. So it's complicated because the units for a moment of inertia are always kilograms times meters squared. So the units for angular momentum are kilograms times meters squared times, what are the units for angular velocity? Do you remember, Sam? Radians per second. So what I want to do is two different problems. But first, I want to do it translational, blast from the past, momentum. And then I want to show you the same problem done rotation style. So first, let's look at an inelastic collision problem. Let's say you have a cart coming along, and let's say this cart has a mass of 2 kilograms, and it's coming forward at 1 meter per second. And then there's another cart here, which has piled up mass on it. And this one here is 4 kilograms, and it's at rest. And then afterwards, the two carts stick together. and they go off with some combined velocity. Anytime you have a collision, that shouts out conservation of momentum. Take a moment and see if you recall how to do this problem. Bravo. So remember, the mass times velocity of this one plus the mass times velocity of this one equals the mass times velocity when they're stuck together. So 2 kilograms times 1 meter per second plus, this is going to be 0 because it's at rest, equals, now the masses get added up, so it's 6 kilograms times some unknown final velocity. And if you solve for this,
3 meters.
you get 3. No.
No,
Oh, 1/3. Oh, 1/3. Sorry.
Yep.
Wow, you guys are shocked. Yeah, you did.
And of course, we would want to write it as a decimal to show sig figs. So 2 sig figs, that would be 0.33 meters per second. So you remember those, yes?
Yeah.
Yep.
All right, so now we're going to do the same problem over rotational style. It's an inelastic collision rotational style. Whoops, wrong button. Oh.
I'm sorry. Definitely missed that. Maybe we should. There's a gnat.
That's where I was trying from away.
Weird. Dude, he was calling me.
What? That's what I was talking
In
about.
your fault. Yeah, yeah, wow.
That's why I can't
Right.
say.
Shh, 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 shh. So here we have this bottom disk that's spinning, and we're going to drop this top disk and plunk it down on the bottom disk that's spinning round and round. So this is like the before scene. And then the after scene is going to look like this. The two are going to stick together and spin together. And the question is, after you drop that top one on the bottom one, what's their new combined final angular velocity? So let me demonstrate. I've got this turntable down here. That's going to be spinning. I'm going to take a second one. I don't have a solid disk, but let's just pretend this is a solid disk. And I'm going to put it on top. And while the bottom one's spinning, I'm going to drop this one. Yes? Now, in order to help with the impact, I just brought this in. Maybe it won't be so clanky. Now, when I'm spinning this one, and I take the top one and I drop it on it, what do we expect to happen to the new final velocity, or angular velocity?
Slow down.
It should slow down, and let's see if it happens. Wasn't that dramatic, was it?
Because it was too slow. Hey.
The bottom one has a bigger radius and a bigger mass, so it has a lot more angular momentum. This one didn't have as much angular momentum, so it didn't influence it as much. But nonetheless, you get the idea. So take a moment, try to calculate what that new one would be using the same techniques that you used with the first problem. But now you're just doing it rotational style. Oh, these are cylinders. So remember, for a cylinder, the moment of inertia is 1/2 mr squared. Instead of being m times v plus m times v equals m times v, what's the formula going to look like this time? Parth? Bravo. I times w plus I times w is going to equal to I times w. But this one here being dropped, it's not spinning at all, so it doesn't have an angular velocity. This one down here, it is spinning, so its moment of inertia would be 1/2 mr squared. Its omega would be, yeah, omega, whatever that is. So this would be 1/2 4 kilograms times 0.15 meters squared times 4 radians per second squared.
Is it
Now-
15? Did you put 15 or point 15?
Point,
It was 0.15, but it's not.
point.
It has like a 6 kilogram.
Now, remember how you just added the two masses together in the initial translational problem? Here, you're just going to add the moments of inertia together. So the total I here of this guy here is just going to equal I1 plus I2 times their final angular velocity. So what you're going to have to do is 1/2 mr squared for the top guy plus 1/2 mr squared for the bottom guy. So it's a lot of math here, but it's just like adding masses, but now we're adding moments of inertia. 1/2 times 2 kilograms times 0.10 meter squared plus 1/2 times 4 kilograms times 0.15 meters squared. And I'm going to put that in brackets. And it's going to be that whole thing times the final angular velocity. Did anyone happen to crunch that out?
Oh, for the final?
Yeah.
I got 3.3.
Yeah, I also.
Yeah, probably.
And that's what we expected, because at first it was spinning 4 radians per, oh, this should be second. I don't know why I said second squared. 4 radians per second. And look, I did meters per second up here. This should be radians per second. So we expect it to slow down. Okay, again, I want to do a second problem, but first I want to do a translational style to kind of like wake you up to the process, and then we'll do it a second time, rotational style. An explosion type problem.
That's over here now. Right there, must be looking for it. Did. Add to it. When you stayed out for the middle, not like feedback review.
Two ice skaters are going along together, and they're moving forward at 2 meters per second squared. And let's say the mass of this second person here is 60 kilograms, and the mass of the first person up here is 40 kilograms. And then they push apart. And this person here has a mass of 60 kilograms, pushes the second person off, and the person with 40 kilograms goes flying forward, let's say 6 meters per second. The question is, what's the final velocity of the first person? So this time, it's m times v equals m times v plus m times v. This time the combined mass is 100 kilograms, and the velocity together was 2 meters per second. And then they explode apart, and you have 60 kilograms times some unknown final velocity plus 40 kilograms times the 6 meters per second. Did anyone crunch that out and get that final velocity of the first person?
Negative 0.66. Yes.
If I round to 2 sig figs,
4? No, there's no 4.
there's no 4.
It's just
Negative
0.67.
Yeah.
So the person pushed so hard that they're going to end up going back in the opposite direction. Now we're running a little short on time, so tomorrow when you come in, the first thing we're going to do is a rotational problem that's similar to this.